pleasure to be here. I'm glad I made it. I'm glad we all made it, given the volcanic excitement over the last weekend. And I'm going to talk about from beast machines to dream machines. It's really a talk, of course, given this conference, it's really a talk about consciousness. So I wanted to start just with a definition. It's very hard, as we know, to come up with a precise, a consensus definition of what consciousness is. But I like to start with a very familiar, hopefully to many of you, definition of consciousness that comes from Thomas Nagel, the philosopher. And he says an organism has conscious mental states if and only if there is something it is like to be that organism. I think what he's getting at here is that it feels like something to be me. It feels like something to be each one of you. It feels like something to be a kangaroo, or in Nagel's famous paper, it feels like something to be a bat, although only a bat will ever know what that feels like. But it doesn't feel like anything to be this table, to be this microphone, or I would argue to be this iPhone, though some people might disagree with that one. But this definition of consciousness, I think, is useful because it's intuitive. And intuitively, we all know what consciousness is. It's what we lose when we go into a dreamless sleep or under general anesthesia, and it's what comes back on the other side. And when we open our eyes in the morning, there's more than just stuff happening inside a brain. I mean, there's an experiential felt quality to the nature of conscious experience. And this definition is also useful because of what it doesn't say. I think there's sometimes a temptation to conflate consciousness with other things, like intelligence or language, or the explicit sense of personal identity. But consciousness at its most fundamental is none of those things. It's simply any kind of experience whatsoever. So that's a kind of, I think, an intuitive starting point from which we can build understanding. And faced with that kind of definition, of course, comes the challenge, the problem, which is why we're all here. It's how and why does it happen? How and why does this mess of electrified pate inside our skulls give rise to consciousness in the first place? How does that happen? There's been many articulations of this problem over thousands of years. I think the one that's most common these days, and again, I think originated at one of these conferences many years ago, is from Dave Chalmers, who's going to be here later this week. And he, in his hard problem of consciousness, puts it like this. He says, it is widely agreed that experience arises from a physical basis, but we have no good explanation of how, or why and how it so arises. Why should physical processing give rise to a rich inner life at all? It seems objectively unreasonable that it should, and yet it does. That's the hard problem of consciousness, and I think the intuition in driving this is that we neuroscientists could get on with all the so-called easy problems, figuring out how the brain's circuits transform inputs into outputs, how they control the body, how they form perceptions, all these kinds of things. And at the end of neuroscience, we would still be in the dark about how and why there is consciousness happening at all. The easy problems integrated don't amount to a solution of the hard problem. And there are many responses to this apparent mystery, and I agree, actually, that it seems like there's a big mystery here. There's this feeling that consciousness is not the kind of thing that's amenable to a material explanation in terms of brains and bodies. This is what Dave's recently been calling the meta-problem of consciousness, which I think is really interesting. And in the face of this apparent mystery, you can reach for some sort of radical solutions. You can reach for panpsychism and say that consciousness is in fact fundamental and ubiquitous. It's everywhere and in everything, so you don't need to explain how it comes about. This is kind of interesting, but I think not very productive. On the other hand, you could be a very strong illusionist and say we're totally mistaken that there's a problem at all. Consciousness doesn't in fact exist. All that's going on is brain processes. Again, I think it's a more interesting response, but taken too far, I think it denies the phenomenon that we're trying to explain, which is the existence, the nature of consciousness itself. So in between these responses, the approach that I want to explore with you today is actually, it's something that many of us will be doing anyway. It's certainly something that in cognitive neuroscience people just do. And to put a name to it, slightly to have a friendly dig at Dave, I've called it the real problem of consciousness. And this is the problem of saying, okay, consciousness exists. Let's just accept that conscious experiences happen. And we know they depend in intimate and lawful ways on things happening in the brain and the body. So instead of just looking for correlations between these things, as has been sort of standard in cognitive neuroscience, looking for the neural correlates of consciousness, let's try to build explanatory bridges, explain the properties that these conscious experiences have in terms of things happening in brains and bodies. So here's it stated a little bit more formally. How can mechanisms and processes in the brain and the body explain, predict, and control properties of consciousness, functional and phenomenological? Explain, predict, and control. I mean, this is arguably what scientific explanations allow us to do. They allow us to explain why particular phenomena happen, predict when they're going to happen, and ideally control when they happen. They don't always have to explain why a phenomenon is part of the universe in the first place. I mean, physics allows us to explain, predict, and control many aspects of the universe, but it doesn't tell us why there's something to explain in the first place. Explain, predict, and control. And functional and phenomenological, very important here, because a lot of cognitive neuroscience is about explaining the functional properties of systems. We can look at what we can do in virtue of being conscious versus unconscious. But there's also the phenomenological, experiential aspects to it. So visual experiences feel a particular way. They have a character of spatiality, for instance. Certain things like colors appear in visual experience and not in other forms of experience. Emotional experiences are very different. So building bridges that explain these properties, that's the kind of the bread and butter of this approach. It's not a new approach, let me just really emphasize that. But it's neither the hard problem, because we're not trying to explain how and why consciousness is part of the universe. And it's not the easy problem either, because we're not sweeping consciousness under the carpet and just focusing on the brain as a something that achieves functions. But it's not new. It inherits very, very closely from the old tradition of neurophenomenology, pioneered by people like Francisco Varela in the 90s, which was all about building these explanatory mappings between brains and conscious experiences. And Dave Chalmers himself talked about the mapping problem, which is also quite similar, going beyond correlations toward explanations. Now, the hope in doing this, and I want to give you some hints that this might work in the end, is that by following this approach, one doesn't solve the hard problem of consciousness, but one dissolves it. So that bit by bit, as we build these explanatory bridges, the sense that consciousness remains this deep, intractable mystery will gradually fade away and, I hope, let's see, disappear in a puff of metaphysical smoke. Now, there's a kind of historical parallel for this. It's not a perfect one, but it's how scientists understood life. Now, it wasn't that long ago, maybe 150 years ago or something. Surprisingly recently, I found that the philosophy of vitalism was still quite dominant. And this was the idea that life could not be explained in terms of physics and chemistry. There had to be something else. There had to be something perhaps almost supernatural, an élan vital, a divine spark, a spark of life that could create the living from the non-living, that explained that difference. There was a kind of hard problem of life too. But of course, biologists didn't say that life doesn't exist. They didn't identify the spark of life, and they didn't say life is everywhere in the universe. What biologists did was say, okay, living things have particular properties, metabolism, homeostasis, reproduction. Let's explain those properties in terms of physics and chemistry. And bit by bit, the hard problem of life was dissolved. It wasn't solved. And although we don't understand everything about life, there's no longer a conceptual mystery that life is beyond the reach of physics, chemistry, and of course now biology. This is not a perfect parallel. Of course, we're not so far along the road, and there are some other clear differences. One of the obvious differences is that when we're trying to understand life, by looking at frogs, for instance, that's what you can do to understand life. You can put a frog on a table, and you can observe it in all sorts of ways, and you get publicly shareable objective data about what's happening in the frog. Consciousness is, of course, different and more challenging in this regard. Conscious experiences are intrinsically private and subjective. Back to Nagel's point, nobody else can know what it's like to be a bat, let alone somebody else, although we'll come to that later on. So the data for consciousness science, or at least the data that speak to phenomenology, are private and subjective. Does this mean a science of consciousness is hamstrung, is impossible? I don't think so. I think it just means the relevant data are harder to acquire, but there are ways to do it by, psychologists have been doing this since the 19th century, getting subjective reports about what's going on. So I don't see it's a fundamental objective, and we'll sort of see some examples of this now. So this is the overall approach. Bit by bit, build these bridges, and the hard problem, we hope, will take care of itself. Maybe it will, maybe it won't. So what are the properties of consciousness? There are properties of life. What are the equivalent properties of consciousness? Well, there are many ways to cut this cake, and here's one way of doing it. This is my generally preferred way, and I'd like to think of consciousness in roughly 3 different ways: level, content, and self. And these are not totally independent things. It's a rather kind of pragmatic, heuristic approach to think about consciousness in this way. But broadly speaking, conscious level speaks to global states of consciousness. Differences between wakeful awareness, like now, sleep, anesthesia, coma, perhaps the psychedelic state, states where consciousness, everything about consciousness changes in sort of somewhat similar ways. Either goes away, comes back, and so on. So we can think about what's happening in the brain that explains and predicts, controls changes in conscious level. Then there's conscious content. When you're conscious of something. Right now, the sound of my voice, the slide in front of you, feelings of thirst or boredom, I don't know. But there's particular things that populate your conscious experience in the here and now. These are the contents of consciousness. How are these generated? How are these shaped? Why are they different from each other? A very important subset of conscious content is conscious self, the specific experience of being you or being me. The self here is not the thing that does the perceiving. The self is a kind of conscious content, a kind of perception too. So what explains the specific experience of being you or being me? So these are, I think, a pragmatic way to divide up the problem. And in the rest of this talk, I'm going to just give you a brief flavor of each of these dimensions and what we can do with them. So I'll start with conscious level, global states of consciousness. And the first thing to say here is that these global states, conscious level, is not the same thing as physiological arousal or wakefulness. Like, often they correlate, so this is showing wakefulness against conscious level. Often they correlate, so if you're awake compared to asleep, in a deep sleep you are both less conscious and less awake. But importantly, you can go off the diagonal in both directions. So when you're dreaming, you're asleep, but you're clearly conscious because dreams are conscious. And other states of sleep too actually have quite conscious contents, often even in slow wave sleep. And then you can go off the diagonal in the other way too, where in pathological states such as the vegetative state, people can be awake, but they are, by the clinical definition, they are not aware of anything. So the two things can dissociate. So we need to look for measures, explanations of conscious level that track consciousness itself and not merely wakefulness or physiological arousal. There's one approach that seems to be particularly productive in this, and this is based on measures of brain complexity. Now, this has been an interesting class of measures because one aspect of consciousness that applies to probably all conscious experiences is that they're interestingly complex. They bring together lots of different sources lots of different kinds of information in unified scenes, and as people like Giulio Tononi have repeatedly emphasized, every conscious experience is informative in the sense that it's different from every other conscious experience you've ever had or ever will have. Rules out an enormous repertoire of alternative possible experiences, which mathematically is what we mean when we talk about information. So all conscious experiences seem to have this character. Can we begin to find correlates of that property in the brain? Well, a very blunt measure of this, an initial start, is from these measures of what's called Lempel-Ziv complexity. This is not a full-blown measure of complexity, but it's a start. Lempel-Ziv complexity is actually the algorithm that is used to compress photos into JPEGs. What it does is it looks for the number of repeated patterns in a signal, and it could be a digital photo, it could be brain activity. And it basically counts the number, the size of the alphabet of distinct patterns you find in a signal. So it's really a measure of the diversity or predictability in opposite directions of a signal. So it's related to what intuitively you might think of complexity, but only really one side of it, like how many different patterns are there, not how integrated they all are. There are ways the benefit is very easy to calculate, that I won't go through it, but there are well-established algorithms that you can use to apply to a signal to give you an estimate of the number of distinct patterns in it. So it turns out if you apply this measure of complexity to neurophysiological brain data, you get pretty good, robust measures of global states of consciousness. This was work from quite a long time ago with my colleagues and students at Sussex, Adam Barrett and Michael Shatner. So in anesthesia, for instance, the level of complexity goes down under anesthesia, which means the brain gets more predictable under anesthesia. There are fewer distinct patterns of activity in the anesthetized brain than in the aware brain. This was a collaboration with Marcello Massimini, who's in Milan in Italy. We used intracranial data here to again measure complexity. And what's, I think, worth pointing out here is that we also now look at, this is sleep, but we're looking at REM sleep. So levels of complexity during REM sleep are basically the same as wakeful awareness, but they go down in early non-REM sleep, which is where consciousness is most likely to be absent. So this measure is tracking consciousness, not wakefulness, which I think is an appeal, that's a useful demonstration of that. Finally, a few years ago, we applied this measure to data from the Imperial College group, who'd been collecting amazing data sets of the brain under various psychedelic manipulations, so LSD, psilocybin, and ketamine. This is just one from LSD, and what we found was a reliable increase in signal diversity in the psychedelic state, so the opposite of the loss of consciousness. Here, there are more distinct, diverse patterns, a higher signal diversity in the brain under psychedelics, this was true for all the psychedelics, than there is in normal waking state. You can kind of intuitively think this makes sense in psychedelic experience, that you can describe it as maybe a bit more varied, more things going on, more connections being made, maybe a bit less predictable than your normal experience. So there are links here between the phenomenology and the measure. They're initial links, but there are links. So this is work that's powerful partly because it's very empirically robust, so that helps. But it's not a full measure of the complexity of brain data. I sort of hinted earlier that complexity has these two components. It has informativeness, many different patterns, but somehow they're also brought together in a unified scene when we're conscious. Conscious experiences are always, at least we think so, unified. Some argument about that, but let's take it as a start point. Perhaps the most influential theory hereabouts is integrated information theory, which proposes measures of integrated information, called phi, which bring together both number of distinct patterns in information and how they're integrated. And there are a whole family of different measures of integrated information. Some of them are very hard to calculate, but they make very strong claims that that is consciousness. So they're actually addressing the hard problem, if you like, that this is consciousness. Our approach at Sussex is to take a slightly weaker approach and come up with measures of integrated information that we don't claim are identical to consciousness, but which still track these fundamental aspects of signals being both diverse but also integrated. So things that reflect this balance of information integration. So we've got a few of these measures now summarized, for instance, in this trends paper. They are harder to apply to data. They're much more fragile, so I don't have reliable data to show you as I did for the previous measure. But this is the sort of trajectory I think we can go. We can start to build these explanatory bridges bit by bit, rather than biting off the whole thing at once. Just to give you a clue of where we're going next, there's another concept that's often associated with consciousness in general, which is emergence. This idea that in some systems, like in this flock of birds, but perhaps also in our brain activity, there's something more than the sum of the parts happening here. There's something to the flock that seems to be more than just the summation of the trajectory of the individual birds. And you can think in some ways of conscious experiences being more than the sum of all the activities of the neurons or brain regions that are involved. There's something apparently seemingly emergent about it. But again, there are two ways to think about emergence. You've got this idea of strong emergence, where some property is fundamentally irreducible to its underlying components. This, I think, is, I sort of call it spooky style emergence, and it's pretty useless because you can't really do much with it. But again, there's a weaker form of emergence which I think is really helpful, which is how do we explain things that seem to be more than the sum of their parts, like the flock of birds. There's no mystery that the flock of birds is made up of individual birds, but there's still a difference between birds that flock and those that don't. And how can we explain that difference? Can we measure it? And can we, is something like that happening in the brain when conscious experiences are happening too? So it's a way of tracking this relation rather than making a grand claim about what consciousness is. And again, I won't go through the details, but there are many various different approaches to measuring emergence that have been worked on. I've been working on them since 2010. There are now a number of different approaches that allow us to identify what's emergent and quantify how emergent it is. And I think these are all useful tools for approaching things like how do global states of brain activity relate to global states of consciousness. And there might be interesting applications for this kind of thing too. So in another recent collaboration with the philosopher Tim Bain and Marcello Massimini, we wondered about whether there could be such things as islands of awareness. And people talk about organoids these days, these little lab-grown collections of neurons grown from human stem cells in a dish. They're made of biological stuff. Are they conscious? Well, they don't get any sensory input or motor output. But how do we even know? So things like these measures, I'm not saying they would give us the definitive truth, but they're interesting because we can apply them to systems without those systems having to behave or give us any kind of report. There's a sort of review about islands of awareness there. So I'm going to skip quite quickly. We can come back in the Q&A to any aspects of this. I want to move on for the rest of the talk to conscious level and how we experience the world the way we do and the self the way we do. So conscious content and conscious self. And start with conscious content. And the idea here is that your brain is a prediction machine, and that what you see, what you hear, what you feel are not sort of passive registrations of an external objective reality, but they are always and everywhere active constructions that are reined in by sensory signals coming from the world. Controlled hallucinations, too, in a phrase that I quite like to use. Now, again, this is a very old idea. You can trace it back as far as you like. You can certainly trace it back to Plato and his allegory of the cave. In Plato's cave, there are prisoners. They're chained to the wall of the cave, and all they see are shadows cast on the wall by firelight, and the shadows reflect what's going on outside the cave. But the prisoners take the shadows to be real because that's all they have access to. They make up stories about the shadows and so on. And actually, when one prisoner escapes and leaves the cave and sees what's going on and then comes back in to tell the others, they want to kill him because they don't want to know. The shadows are what's real. Now, instead of skipping over a couple of thousand years, merrily, coming to the present day, instead of prisoners in a cave, think about your brain trapped in your skull. Now it's dark in there. It's silent. There's no noise. There's no light. It's completely dark, completely silent. All you've got to go on as a brain when trying to figure out what's out there in the world are noisy and ambiguous electrical signals coming through the sensory modalities that only indirectly reflect what's out there or in here in the body. So to make sense of these signals, the brain has to bring to bear its prior knowledge or expectations about what's going on in order to form a best guess about the causes of these sensory signals. And the idea I want to suggest is that is what we experience, not a readout of the sensory signals, but the brain's best guess of the causes of those sensory signals. The brain doesn't hear sound or see light. What we experience is the brain's best guess of the causes of signals which themselves are not sound-like, they're not light-like, they're just energy in different forms. So what we experience comes from the inside out more than the outside in. Now, there are many fun demonstrations, at least, of the importance of the brain's prior expectations in how they shape what we experience. This is one of my favorites. This is the hollow mask illusion. How many people know the hollow mask illusion here? I'm guessing quite a few. So in this hollow mask illusion, there is obviously it's a movie. It works with a real mask as well, which is even more fun because the eyes follow you around. But in the hollow mask illusion, what's happening is the mask rotates, and at a certain point about now, we sort of see it rotating in both directions at once. Now, face is a very, very important stimuli for human beings. The whole history of our brains over evolutionary time has been very, very bound up with the importance of recognizing faces and expressions and so on. And every face that our brain and our ancestors' brains has ever seen points outwards, with the nose pointing out. So we have a very strong expectation that that's what faces are. They always point outwards. This expectation that the brain has is so strong that it would rather reach the conclusion that the face, this mask, is rotating in two different directions at once than that it's in wrong way round, concave face. So this is, I think, a powerful demonstration of the power of the brain's expectations. Now, what's going on sort of under the hood here? There are many ways to think about this, but the obvious framework to think about this is in terms of Bayesian inference, which is a way, very generally, of reasoning under conditions of uncertainty. It's applicable to all kinds of things, like looking for hidden nuclear submarines, to figuring out the likelihood that you've got a nasty disease when you get a positive test, something like that. And the idea of Bayesian inference is simply a way of taking what you know now, the prior, and some new information, the likelihood, and figuring out what you should believe next, the posterior. And they're all weighted by reliability. So if you're very confident in the prior belief and you get some evidence that's different, then you don't shift your very far to the posterior. But this is the kind of optimal way of reasoning under uncertainty. And you can imagine that that is what the brain is doing when it's doing perception, that it's using incoming sensory data, the likelihood, to update its prior beliefs about the way the world is, to form posteriors in this continuous, ever-unfolding cycle. Now, the first person, to my knowledge, to really propose this as a theory of what's actually happening in perception was Hermann von Helmholtz, to put it on a sort of neural basis. And he had this theory of unconscious inference. He said, that's what's happening all the time. The brain is making inferences about what's going on in the world, and they're unconscious. We're not aware that our brain is doing this. We're only aware of the outcome of the best guess itself. So he called it unconscious inference. Now, thinking this way, I think really challenges our intuitive feeling about how perception works. I mean, this is a standard picture of a visual system, the sort of thing that I certainly saw when I was reading textbooks when I was doing my undergrad 30 years ago. And in this kind of classical view of perception, all the heavy lifting is done in this bottom-up direction. The brain, there are sensory signals that come in from the world, they enter the visual cortex, they move higher and higher through the visual cortex, and things of different complexity, features of different complexity are extracted as we get deeper into the brain, with early stages pulling out low-level features like edges and lines, and higher level areas, deeper areas, pulling out combinations of features like faces and object parts. Now, there might be some top-down finessing of this process in this classical view, but really the important heavy lifting is done in this outside-in, bottom-up direction. Now, the prediction machine, the Bayesian view, I think changes this quite a lot. And in the sort of standard implementation of this, called predictive processing or predictive coding, what we have, instead of the heavy lifting done in the bottom-up direction, we've got this continual exchange of predictions and prediction errors. So predictions, these blue arrows, they just flow from the inside out. They flow down through the brain back out to the sensory surfaces. And then there are sensory signals which constitute prediction errors, just reporting the difference between what the brain expects and what it gets at every level of processing in the perceptual hierarchies. And it turns out that if the brain follows a simple principle of just minimizing prediction errors everywhere and all the time, it will approximate Bayesian inference. It will be doing Bayesian inference on the causes of its sensory signals. So it's a way for the brain to actually implement this challenging problem. And now the perceptual heavy lifting is done in the top-down direction. These are the predictions. And the sensory signals are just calibrating these predictions, keeping them tied to the world in useful ways. So I think that's the core conceptual message, that perceptual content is conveyed by top-down predictions, and bottom-up signals, in this view, convey the prediction errors. Now, things are not always that simple. One of the nice things about this framework is it's very powerful, it's very flexible. So we might initially associate conscious perceptions with these top-down predictions, but there are actually many ways to think about how predictive inference might be implemented in the brain. This is just a recent piece of work that we've done at Sussex, led by PhD student Alec Chance, called hybrid predictive coding. And in hybrid predictive coding, we have predictions and prediction errors flowing in both directions, bottom up and top down, but at different time scales. So this is it's motivated by some work in machine learning that takes different kinds of inference, fast or amortized inference, where a system learns a mapping directly from some data to the optimal posterior, the best Bayesian best guess, and iterative inference, where you have this exchange of predictions and prediction errors. And it turns out that you can combine these two ways of inferring and learning in a single architecture, which naturally balances this bottom-up and top-down predictions and prediction errors. Now, this is both an interesting machine learning architecture, but I think it also, and this is work we haven't done yet, but I think it has some relevance to phenomenology too. Because, for instance, we have an interesting difference between the immediate experience of context, what we might call gist perception. We know we're in a lecture theatre right now. We don't know the details, but we know we're in a lecture theatre. That kind of perception can happen very quickly. But then there's a focused, detailed kind of perceptual experience when we focus on particular people, figure out what's going on. So it might be that these different kinds of phenomenology associate with these different kinds of predictive inference. So again, it's a way of building bridges between aspects of phenomenology and processes in the brain. But again, it's promissory. We've just developed the architecture, not tested it against, in experiments yet. So the thing to say here is predictive processing, as I've mentioned it, this exchange of predictions and prediction errors, is not, at least in my view, not a theory of consciousness. Some people say that it is. I think it's rather a general theory of perception and action and cognition and so on. And it can be used to explain properties of phenomenology in terms of underlying mechanisms in the style of the real problem. So it's rather a theory for consciousness science rather than a theory of consciousness itself, the way I see it. And I won't go into this too long because I don't have time, but that point we expanded on a little bit with Tim Bain, the philosopher, in a recent review in Nature Neuroscience Reviews on theories of consciousness, where we cover, I think, the four most prominent classes of theories. So higher order theories, global workspace theories, integrated information theories, and predictive processing or re-entry theories. Seeing how they relate to each other in their assumptions and what kinds of things they attempt to explain. And they're all quite different, which is why it's quite hard to directly compare them against each other. There are, of course, many other theories I just wanted to mention. We had to, so we've got a table. That's one of the striking things about this field at the moment. There's such a rich space of theories that I think there's a real need to begin to refine this space and figure out what the common principles are among some of them and what we can begin to winnow down. Okay, so what kind of evidence would support this predictive brain idea? So in an older, this is just to give you a flavor of the kind of studies that we can do with this. This is an experiment carried out with my postdoc at the time, Yai Pinto, who's now in Amsterdam with his own group. And what we did here was we used a technique called continuous flash suppression to basically, people would experience through one eye, they would see this image arising out of darkness, and in the other eye, they'd see this changing Mondrian of colored shapes fading back into darkness. And for each participant in this, when the brain's trying to mix these two things, what you experience is initially the high contrast colored blobs, and then at some point the image breaks through. And the image is a face here, but it could be either a face or a house. And what we do also, we give people a cue, the word, coming up, face, but that could be a house, the word house too. So we give the brain an expectation, and then we ask the question, how does the expectation affect how quickly and how accurately the image breaks through into conscious perception? And what we find over a series of experiments is that people consciously see more accurately and more quickly the image when it's what they're expecting compared to when it's what they're not expecting, which is what you would expect on this kind of theory, right? That when the brain's predictions align with the data, there's a quicker match. So you consciously see it more quickly. So that's one kind of experiment in favor of this view. Of course, it's not direct proof of it. It's only one among many experiments. We recently extended this experiment, I just wanted to mention, into memory, which I think is a really interesting line of work because memory, especially our immediate memory of the past, is very tied up with our conscious experience of the present. In fact, there's this term from, I think it's James and my old boss Edelman, certainly talked about the remembered present as a way of thinking about our conscious experience in the now. So what we did here, without going into detail, was we had people basically try and detect changes between two arrays of letters and indicate how confident they were in their choice. And sometimes the letters changed, sometimes they didn't. But what basically we showed was that as the time interval increased between the two arrays of letters, so as people were relying more and more on their memory, we saw more errors in confusions between. So people were more likely to remember what they expected to appear than what was actually there. And we modulated expectations here by having letters that were either the right way around, which is what people would expect, or mirror letters, inverted letters, which people didn't expect. So the summary of this is that even our immediate memory, like a few seconds ago, becomes increasingly contaminated, if you like, but not necessarily in a bad way, maybe in an adaptive way, by our expectation of what we expected to be then, rather than what we actually perceived at the time. So partly I wanted to mention this because it's the only study I've been involved with which got a mention on the Colbert Report in America, which is like got to be a career highlight. So here's the clip. Just any excuse to show it. They don't mention us anything by name.
Meanwhile, in a new study, scientists have found that human memory may be unreliable after just a few seconds. That headline again. Meanwhile.
That's it. So I'm happy now. So moving on, getting closer to phenomenology, in fact, there are ways to think how can we link this to different kinds of visual experience here. And staying with faces also, there's this common experience I think we've all had where we can see faces where they're not really there, like faces in clouds or faces in the arrangement of windows on a building. The general phenomenon here is called pareidolia, the experience of seeing patterns in things. And the idea, I think, from this perspective is that the brain is always projecting predictions of face and other things too into the sensory data and seeing where they stick. And when they stick a little bit, we experience kind of the shadows of a face. And so we're seeing part of the brain's predictions here that surface in our experience. Now, taking this like everyday examples and seeing where we can go with it, we come to what's becoming called this approach of computational neurophenomenology, the use of computational models to bridge this gap between neural mechanism and experience. So one thing we've been doing for a while in this line is using visual deep neural networks used for classifying objects and images to do visual image processing and so on. And then using them in slightly interesting ways. So this is a pretty old hat neural network now. It was one of the original deep neural networks, AlexNet. It's very good at classifying objects in images. You show it the image, it will tell you what it's a dog and what kind of dog and so on. And the activity flows in this kind of bottom-up direction when it's being used in classification mode from the sensory data to the output. But the clever people at Google invented this algorithm called Deep Dream shortly afterwards. And what happens in Deep Dream is you fix the output, let's say to dog, and then you feed the activity back through the network and update the image until it settles into a stable state. So intuitively, it's a little bit like projecting a prediction of dog back into the sensory data, as if the brain had an overly strong expectation to see dog everywhere. Now, with my postdoc, Keisuke Suzuki at the time, we took and adapted this algorithm and applied it to panoramic video that we'd taken at Sussex campus. And then we took people and we gave them a virtual reality headset so they could look around them in this movie panoramic video of Sussex campus that had been deep dreamed in a particular way. And just want to give you a sense of this. It's more powerful with the headset on, but this is Sussex campus transformed through this algorithm when there's a strong prediction to see dog. And you can see there's a few too many dogs here than normal, appearing out of all aspects of the scene. So we mainly did this for fun. I mean, we did some sort of experiments on time perception as well. But the take home for me of this was, what is this doing? It's not a model of a particular kind of behavior. It's a model of a particular kind of experience. Some people say it's a bit psychedelic. I think, well, a little bit, but not really. But it's definitely a model of some sort of altered phenomenology. So what we've been doing since then is trying to be more specific and take different kinds of hallucination and see if we can model the differences between these different kinds of visual experience. So Parkinson's disease, People often have visual hallucinations. They can be quite complex and spontaneous. Charles Bonnet syndrome, visual loss. People have other kinds of hallucinations, often involving simple patterns, but also little people wandering around the room, which are almost never disturbing to the people, interestingly. And then there are, of course, psychedelic hallucinations, which seem to be often transformations of existing sensory input. Clouds turn into animals and so on. And they can be simple or complex. So again, just a very quick survey with Kesuke, David, and Alec. We took a more complicated, sophisticated neural network, which not only classifies images, but has a generative component, which is able to generate synthetic images in different categories. And basically, by parameterizing this network in different ways, we're able to simulate what we think are visual hallucinations corresponding to these different categories of etiology where they came from. So for instance, these are all input images, and they all get transformed in different ways to end up with models of different kinds of hallucination. So a volcano up at the top, topically. And what we then did, modeling the hallucinations this way, we can analyze the image statistics and so on, but what we did was we went to people who actually have lived experience of these hallucinations. We asked them which output from the model best reflects what happens to you. And what we're finding, I don't have a good graphic summary, unfortunately, what we're finding is basically people choose the image category that reflects what we designed the model for. So people with Parkinson's disease choose the images generated by our model of Parkinson's. So it's a kind of way of closing the loop here. We can get a handle on what the computational mechanisms are that underpin the specific kind of hallucination that arises in different conditions. So I'll be interested to follow the hallucination session this afternoon. I think it's tomorrow, isn't it? It's tomorrow. To learn more about that. Okay, so moving towards the end, the kind of idea here, we can think about hallucination as uncontrolled perception. It's what happens when the brain's best guesses about the world lose their grip on their causes in the world. And by the same token, we can think of normal perception in the here and now as a controlled hallucination, in which the brain's best guesses are reined in by sensory signals from the world in ways not determined by their accuracy, but determined by their utility for the organism. We see things in ways that are useful for us in terms of guiding our behavior. Okay, so the last thing I wanted to talk about in this decomposition of consciousness is the self. Now, the idea, the straw self idea to put up and then break down at the beginning is this one, that there's a world out there and the self is this little mini-me inside my head that is doing the perceiving, receiving all the sensory data, figuring out its causes, deciding what to do next, and then doing something. Sense, think, act, as the good old-fashioned AI framework had it. This might seem how things are, but I don't think it is. And rather than thinking of the self as a thing that does the perception, going back in philosophy to Hume at least, we can think of the self as a kind of perception itself. The self is not the thing that does the perceiving, it's a bundle, a collection of perceptions. And the first clue that this might be a productive way of thinking about self is that there are many ways in which we experience being a self. There's the bodily self, the experience of being and having a body. There's the perspectival self, the experience of seeing the world from a first-person point of view. The volitional self, the experience of free will. And the narrative self, the experience of being a continuous individual over time with a set of memories and plans for the future. And the social self, the experience of the self that's refracted through the minds of others. Now, I think all of these can be explained in terms of perceptual predictions of different kinds, but I want to focus on the bodily self in what remains of this talk. And the idea here is, again, that the experience of what is and what is not the body is not to be taken for granted, and it's not just read out from sensory signals coming from the body. It's a kind of best guess. It's a kind of perceptual inference. And there's one experiment which I think is a very neat demonstration of this general concept, and this is, of course, the rubber hand illusion. Now, how many have seen the rubber hand illusion? I'm assuming pretty much everybody. Probably everybody. It's always worth showing again. So in the rubber hand illusion, the guy in blue, his real hand is hidden from sight behind this partition. His fake hand, the fake hand is in front of him, in a position where the normal hand might plausibly be. And the experimenter in green is stroking both hands in synchrony with a paintbrush. And after a while, for most people, but not all, this weird sensation develops wherein the fake hand feels like almost part of the body. It's never completely convincing, you never really believe it is, but it begins to be this sort of slightly odd, uncanny feeling. And so this is what it looks like in practice. There are many ways to test whether it's working, but there's one way in particular which I think is certainly the most entertaining. Always fun to try at home, that one. But the standard story for this is that, yes, the brain is seeing touch on a fake hand. It's feeling touch because its real hand is being touched. And so puts these things together and says, oh, well, it doesn't look like my hand, but whatever. That's the most likely explanation. But I think there's something else going on. And this is something that might have more general implications. This really came from work by postdoc Pete Lush at Sussex, who noticed this huge variability in responses to the rubber hand illusion and thought that, hold on a minute, in psychology there's this old concept called demand characteristics. And when you put people in an experimental situation and it's kind of implicitly clear what they should experience, then some people have that experience. They don't necessarily intend to just comply with the experimenter, but they can actually have the experience that is implicitly encouraged by the environment that they're in, which is why in psychological experiments we should always try and control for these demand characteristics, although that's a lesson that has not been particularly well remembered in the intervening decades. And in the rubber hand illusion, it's pretty clear that you're there's a hand. They're saying, is that your hand? And they're stroking the hands. There's a lot of demand characteristic going on in this situation. And Pete reasoned that if this was what's explaining the rubber hand illusion, then the degree to which people experience it should correlate with their hypnotic suggestibility. We all vary in how suggestible we are. It's not a good thing or a bad thing. We just vary in it. It's a stable psychological trait. But the idea is if we are more suggestible, it means our brains are more able to generate experiences according to the context and implicit demands of the situation we're in. And so in a heroic study, he did the rubber hand illusion on 353 people, you can see in the background, and measured rubber hand responses, but also measured hypnotic suggestibility in each of these people. And what we found was a strong correlation between hypnotizability and subjective report that intercepts almost at 0. So this sort of suggests that the majority of what's going on in the rubber hand illusion is not multisensory integration, but it's demand characteristics. So it's still predictions, but it's a top-down prediction that's been created by the overall context rather than the sensory integration itself. So that's kind of interesting, and I'll skip the rest of that. And it's not just the rubber hand illusion. It turns out there are strong correlations in other situations that we might think that involve these kinds of characteristics that shape experience. ASMR, this autonomic median sensory response, some people find it pleasurable to watch videos of people folding handkerchiefs for hours on end. That turns out to be very strongly correlated with hypnotizability. So does this one. The jumping pylon? So some people say they hear sort of something when the pylon hits the ground. Anyone get that? Okay, so you're all highly hypnotizable. Congratulations. So there's this visually evoked auditory response, very technical name, but it turns out to be very strongly correlated with hypnotizability. But not everything does. The Muller-Lyer illusion, very standard visual illusion. The two lines look different lengths, they're the same length, no correlation. So it's a way of partitioning our things that we experience so we can begin to identify the influence of these top-down contextual expectations, because they matter in different ways for different people. But the other lesson is demand characteristics must be controlled for. So to wrap up, or to begin to wrap up, I'm sorry, I've talked a bit about having a body, but there's also this fundamental experience of being a body, of being a flesh and blood living organism with emotions, with moods, and with this basic basal sense of just being alive, being a living body. And this brings to our minds a whole different class of perception. We're used to thinking of perception as in terms of how we respond to the outside world, but there's also interoception, the sense of the body from within, the sense of the physiological condition of the body, things like heart rate, blood pressure, gastric tension, immune system function, endocrine function. These are all things that are critical to keep us alive. And the brain, if you think about it, has no direct access to what's in the body, inside the body, just as it has no direct access to what's out there in the world. It may be a little closer, but all it gets are electrical signals with some other chemicals washing around. So it still has to make an inference about what's going on. And so what you can think of conceptually is it's the same process, the same dance of prediction and prediction error, but now it's all taking place within the body in a process of interoceptive inference. So interoception is what we experience when the brain is making predictions about the causes of signals from in the body. That is also a perceptual prediction. And the idea here is that's what emotion is. That's what mood is. It's perception, predictive perception of the state of the body on the inside. Now, William James and Carl Langer talked about emotion 100 more years ago, about perception of the change in the physiology of the body. So this is really just updating that and wrapping it into this predictive coding story, where we can think that emotions, moods are predictive inferences about the internal state of the body. And to bring us a little back to the start, there's an interesting thing here, which is that interoceptive predictions are less concerned from the brain's perspective with figuring out where things are or what shape they are, much more to do with controlling things. You know, the brain doesn't care where the kidney is, it just cares that it's doing its job. It doesn't care where the heart is, just cares that it's doing its job. And predictions, as any control engineer will tell you, are a great way of controlling systems when they have to stay within very tight bounds, so they don't deviate. And there's many lines of evidence that converge here, which I'll just mention. Active inference, this generalization of predictive coding where we minimize prediction errors through making actions, not just by updating predictions. Cybernetics, the kind of long lost cousin of modern AI, which focused on control and regulation. Owen Holland, who's here, will talk more about this, I'm sure. Ross Ashby in the photo says every good regulator of a system must be a model of that system. Predictions, again, being central to regulating the body. And perhaps the most ambitious formulation of this is Carl Friston's free energy principle, which basically suggests that living organisms or things that persist over time at a certain level of complexity necessarily induce a kind of predictive regulation of their own internal states. All of these things come together then in sort of suggesting that the reason brains are prediction machines in the first place is because of this fundamental imperative to regulate and control the organism. And I think this has some implications for phenomenology. You know, visual predictions, as we've seen, underpin visual experience, where things are, what color they are. But interoceptive predictions care about how it's going, how our control is going. So emotions don't have particular colors, we associate them with colors, but they really have valence. Things are good or bad, or more likely to be good or bad in the future. So at least at a high level, there's an association here with a kind of prediction and a kind of phenomenology. And if you pull on this thread long enough and think really about why did brains evolve to regulate, control the organism, with this imperative for regulation going pretty much right down into individual cells, what it tends to do is it brings consciousness and life much closer together than they might otherwise be, because we can see that this whole point, the whole reason we have predictive perceptions is fundamentally rooted in our nature as living flesh and blood organisms. Now, Descartes said exactly the opposite. You've always got to have a pop at Descartes. Descartes said, probably for reasons of self-preservation, when he was talking about non-human animals, he said that without minds to direct their bodily movements, animals must be regarded as unthinking, unfeeling machines that move like clockwork. The living nature of other animals was irrelevant to whether they possessed consciousness or morally important mental states. But I think entirely the opposite, that we perceive the world around us and ourselves within it, with, through, and because of our living bodies. We are conscious beast machines through and through. So let me summarize, and I'll finish with a couple of very quick implications. Content and self, what we experience is not a passive registration of what's out there, it's an active, top-down, active, creative interpretation of what's going on. This applies to the body as well, both the body as an object in the world, but also the body from within. And predictions about the interior of the body have more to do with control and regulation than figuring out what's there, which corresponds to a different kind of phenomenology. So I'm aware I'm just about out of time, but I want to mention just a couple of very quick implications of this. One is that, and we'll talk about this more in the AI sessions, wetware might be more important than hardware. If these ideas are on the right track, then before we get conscious AI, we might have to have living machines, if consciousness is intimately tied to life in this way. Simulating it might not be enough. And just a few remarks. I mean, there's this common intuition that in the AI community that consciousness is some function of intelligence, that it will just come along for the ride as AI gets smarter. I don't see that assumption as warranted. But if we try to actually actively design conscious systems, which I don't think we should be doing, then there's more uncertainty. There are many different theories, as we've seen. You know, on my kind of ideas, we're far away because we'd have to have living machines first. But maybe I'm probably wrong. Other theories might be right, in which case actually conscious AI is nearer than we might think. And that would be calamitous because we'd build systems that were capable of experience, and things that are capable of experience might be capable of experience suffering that we might not even recognize. So this would be an ethical catastrophe. So I don't think people should be trying to gung-ho build conscious machines. And even machines that impenetrably appear to be conscious will be enormously disruptive. And I think this is very, very near term. We're almost there with large language models. They'll hack our anthropomorphic biases in all kinds of unproductive and unhelpful ways, leading us to make assumptions and predictions about how they behave and distort our circles of moral and ethical concern. So this is the problem I'm really worried about in this space. Machines that give the appearance of being conscious, even though we know they're not. Okay, so there's trouble ahead. Last implication, and then I'm stopping, is more positive. On a more positive note, one implication of this predictive brain view is that we all see the world differently. We see it, we do not see things as they are, as Anil said, but as we are. So even though it seems as though we all share the same world subjectively, we probably don't. Just as we differ on the outside, we all differ on the inside too. Sometimes the differences are large when people hallucinate, but often they can be pretty small. We might not even know they're there. We might be having very different experiences of color, sound right now and not know it because we'll use the same words and because it seems as though we see the world as it is when we don't. Of course, we know the dress, blue and black, white and gold, neither. Okay, fine. So some examples really reveal to us that we can see things differently. But I think it's more general, and I want to leave you with just a call to action. This is a project that I've been working on with Fiona McPherson, who's speaking tomorrow, among others, where we're trying to measure this perceptual diversity to get a real handle on how we each experience a unique environment. So this project is called the Perception Census. We're still collecting data. It'd be lovely if you'd have a go at it and tell your friends. It's a collection of interactive illusions and simple little experiments and questionnaires that allow us to map out this really fairly uncharted space of inner diversity, on many dimensions at once. So we're looking at sound, music, body, time perception, the role of expectations, color, boundaries of perception, lots of different sections. You can do bits, you can leave it, you can come back later. So far we've had about 27,000 people take part from over 100 countries. So we're hoping to make this a really landmark, one-of-a-kind study of perception and how it differs, and help cultivate a greater recognition that we all experience a different world. This came, and I said beast machines to dream machines. This project arose from this project called Dreamachine, which Fiona was also involved with, where we built installations of strobe lights to give people really unexpectedly vivid and powerful visual hallucinations last year. So we had installations in the 4 capital cities in the UK, and I don't have time to talk about it, but we had 40,000 people experience visual hallucinations and ignited their curiosity about the mind, the brain, and consciousness. Just to reinforce to people, it's not something to be taken for granted. It's an everyday miracle that each of us are privileged to enjoy, and there's so much more to discover. These are just pictures that people from the Dreamachine drew, and I'll leave you with those. And thank you for your patience. These are people that helped me, and that's it.